Okay, let's begin. So let me begin by answering Sahbaz's question. So it is indeed true that if a ring is embedded in a field or more generally in an integral domain, then it must be an integral domain. And for that, you don't need anything from last lecture. So this follows from the fact that, so if you have a injective ring homomorphism from some ring to a field or an integral domain more generally, then the image is then this ring, the codomain. So from the ring you started with, that is isomorphic to a subring of this integral domain or field. Yes, by this injective map. And so if two rings are isomorphic, then one is an integral domain if and only if the other one is. And of course, subring of an integral domain is an integral domain, because if product of two elements is non-zero in the ambient ring, then of course it can't be zero in the subring. Yeah. Does that answer your question, Sahbaz? Okay. Good. So let's start. I hope you can see the screen. So last time we were talking about localization or constructing field of fractions. So today we will continue the discussions and we'll talk about local rings and how, and we will also talk about how ideals behave with respect to localization. So more precisely, how the ideals of R and ideals of S inverse R are related. That's what we want to talk about if time permits towards the end. Yeah. So hopefully we'll be able to start the discussion. So last time, last time we saw the definition of localization, and last time we discussed some properties. So one of the properties we saw was that if R is a commutative ring with unity as a multiplicative subset of R, then in this construction S inverse R, elements of S becomes a unit. Yeah. So the precise way of writing it is this natural map phi. Under this natural map phi, the images of elements of S are unit. Yeah. So phi S is a unit in S inverse R for all S in S. Here the natural map is R going to R over 1. And some sort of converse is true in the sense that S inverse R is in some sense the optimal ring, minimal ring with this property, minimal ring in some sense with this property, and that is what is universal called the universal property of localization. So more formal way of presenting it is if F is some map from R to another ring A such that F sends every element of S to a unit, then F has to factor through S inverse R. Yeah. So that means there is a map from S inverse R to A such that this composition F is something composed F tilde composed phi, where phi was the natural map. So that is what universal theorem, universal property of localization is. And in fact, F tilde is unique. Okay. So so let R be a commutative ring with unity. S contained in R be a multiplicative subset of R. Let F from R to A be a ring homomorphism, where A is a commutative ring with unity such that for all S in S, Fs is a unit in A. Then there exists a unique ring homomorphism F tilde from S inverse R to A such that F tilde composed phi is F. Okay, which pictorially you can write it. Yeah, there's something wrong in this thing. Yeah. So this I copied from the other one, so there must be something wrong here as well. So it should be S inverse R. Okay. So S inverse phi anyway, we haven't defined such a thing yet. Yeah, so there is a natural map from R to S inverse R, and then this F tilde, whose existence we are asserting, and F factors through this. So the F is product of, F is composition of these two. So that's what universal theorem of, so universal property of localization is. And then we saw some basic properties, yeah. So we saw that if 0 belongs to S, then S inverse R is the 0 ring, yeah. So we saw this before the universal property, but let me just list down some of the things which we saw. We saw that if S consists of non-zero divisor, only non-zero divisors of R, meaning every element of S is a non-zero divisor of in R, if and only if uh, the natural map phi from R to S inverse R is injected. Yeah? So if S consists of only non-zero divisor, then you can in fact think of S inverse R as a bigger ring containing R, yeah, in some natural sense. So this map, remember, is the natural map, R going to R over 1. So you can think of R as a subring of S inverse if S consists of only non-zero divisor. In general, we saw that kernel of phi is those elements of the ring R such that S times R is 0 for some S in S. That's why if 0 belongs to R, 0 belongs to S, then of course 0 times R is 0 for every R. Yeah? So that's why the kernel of this map becomes the whole thing, whole ring, and hence S inverse R is the 0 ring. Okay, and then we also defined field of fractions. So I sort of defined it somewhat vaguely. So I'll do it a little more rigorously this time. So I defined it in terms of S inverse R. So best way to approach is define it in this way. One can define it in terms of morphism. So I'll talk about that as well. But one should think of field of fraction as an over ring, a bigger ring containing R. Yeah? So let R be an integral domain. A field K is said to be the field of fractions of R if R is a subring of K and no proper subfield of K contains R. Yeah? So remember, a subfield is going to be a field which a subring of K which happens to be a field. Yeah? So what it says is no proper subfield of K contains R. So that's what field of fractions of R is. So another way is the smallest field containing R in some sense. Yeah, so it's small. So there is no smaller subfield of K which contains R. Okay, and then we showed that if R is an integral domain, S is R minus 0, then this is injective ring homomorphism, and S inverse R is the field of fractions of R where we identify R with phi R. Yeah. So this is the natural map. So you look at so this, and since S consists of non-zero divisors, because we are taking R to be an integral domain, so every non-zero element is a non-zero divisor. So this is injective, and then you look at the image of R, which is R, those elements of the kind R over 1. Yeah, so there is a natural identification. Then the fraction, so the field of fractions of R is basically S inverse R if you do this identification. Okay. Any questions? No. Okay, so let's. So since I messed it up about fraction fields a little bit, let's discuss it a little more about field of fractions. What was the issue? I mean, but one should think in terms of morphism a little later. Since this is a first course, one shouldn't think too much about in terms of morphism at this level. You want to get a good intuition about the subject as well. Yeah? Not get lost in formalism. So yeah, So, for instance, you consider these three rings, Z pi, Zx, and Zd, yeah, where E is this exponentially, yeah. So they are all, these rings are all isomorphic because, we saw that, right? Z pi is isomorphic to Zx and Z is also isomorphic to Z. If you send pi, we saw modulo the fact that pi and E are irrational, so they don't satisfy any non non-zero polynomial equation. Yeah. So these are all isomorphic ring. And if you consider this field Q pi, Qx, and Qe, uh, they are all isomorphic fields. But I mean, you won't call Qx as field of fraction of Z pi, right? You'll call Q pi as field of fraction of um, Z pi, right? But of course, Q pi contains a subring which is isomorphic to Zx, yeah, because Z pi is isomorphic to Z. So that's why when we talk of field of fraction, we always assume that some subring, this is a subring of this, so that there is no confusion. Yeah? You don't want to think of Z as so Q pi as a field of fraction of Z as well. I mean, it will be even more confusing because you can think of both of them in complex numbers. And so that's why you always think of field of fractions as something which contains your original ring. Okay, so that's how we think of it. But if you want to do it formally in terms of morphism, then so these whatever I've written after this, so not just in bracket, but even beyond this, you can sort of ignore for this. This is just for general knowledge. Uh, but you can write you can do this a little more formally. So let R be an integral domain. You can define the field of fractions of R to be an injective ring homomorphism from I from R to K. Yeah. Even the localization, if you do it formally, one has to define localization of R as this ring homomorphism phi. So it's not just the S. So formally, it's the whole ring homomorphism phi from R to S inverse R. So it's not just the object S inverse R, not just the ring S inverse R, but this morphism. Even quotient, when you define R mod I, it comes with this Q map from R to R mod I. So formally, quotient is this map, this ring homomorphism R from R to R mod I. This morphism is called the quotient of R by I. Formally. So in that spirit, the field of fraction is an injective ring homomorphism I from R to K, such that K is a field, and for any subfield K0 of K containing IR, K0 has to be equal to K. That means, in other words, there is no subfield, proper subfield of K containing the image IR. Okay. So this would be a more formal way of saying it if you worry about morphism and stuff. So I gave some transcendental example above, so I thought I'll say that even you can get even non-transcendental examples, right? For instance, Z cube root of 2. This, remember, is isomorphic. So Z cube root of 2 is isomorphic to Z omega times cube root of 2 as well. Okay, so these two rings are isomorphic. Why is that? Because both these rings, you can show both these rings are isomorphic. What's happening? Okay, both these rings are isomorphic to Z adjoint X mod X cube minus 2. Yeah. So both the two rings, they are isomorphic to this third ring. Yeah, maybe I should write it in that so that you can make it out where I'm writing. So both these two rings are isomorphic to this, and their fraction field are so the fraction field of the first guy is cube root of 2. If you are thinking in terms of smallest subfield of C containing Z cube root of 2. Yeah. And fraction field of the second ring is Q adjoin omega cube root of 2, where omega is the complex cube root of unity. And of course, the two fields are also isomorphic by the same reasoning. The two fields are, both the fields are isomorphic to Q adjoin X mod X cube minus 2. Okay. But when we think of field of fractions, we do think of Q cube root of 2 as field of fraction of Z cube root of 2, and the second, but not as field of fraction of Z adjoined omega cube root of 2. Yeah. But they do come, but there is a subring which is isomorphic to this. So this was just the transcendental example. Yeah. So and a field of fractions, I mean, if you define it this way, then you have to argue that the field of fraction is unique up to unique isomorphism. Okay. So what does that mean? So that means that if R you have this embedding R contained in K, and where K is a field of fraction. So if K is a field of so this injection I from R to K is a field of fraction of R, and I prime is another I prime from R to K prime is another field of fraction. Then what you can show is that there exists a unique F from K to K prime, such that F is an isomorphism, and F composed I is I prime. So this you can, so we already know that R to S inverse R is a field of fractions. Yeah, the natural map R to S inverse R. So you can use this and universal theorem of localization to show this this result. Yeah, so you can show that there is a unique isomorphism from K to S inverse R, and you can also show that there is a unique isomorphism from K prime to S inverse R, and then composing them you get a unique isomorphism between K and K prime. So that is how one would prove something like this, that this is unique. Okay. And then I also talked about this result, but we didn't see a proof. So today maybe I'll give you a proof using the universal theorem. So S consists of units, then phi from R to S inverse R, the natural map, which sends, remember, R to R over 1, is an isomorphism. Okay, so this will be another application of universal theorem of localization. Okay. So let me give a proof of this guy, and this this one maybe I'll leave it as an exercise for you guys. Yeah, the previous one. Any questions so far? Okay, so no questions. Okay, so let's see a proof of this thing. Yeah? So we want to show that phi is an isomorphism. So I'll write in black. Okay. So so let's look at this map, identity map from R to R. Yeah. This is a ring homomorphism. I want to show that phi is an isomorphism. Yeah. So first we note that identity is a ring homomorphism, and what does it do? It sends so identity of S is at S itself, and by hypothesis is a unit for all S in S. Yeah. So what does the universal theorem of localization tell us? That this map identity has to factor through phi. Yeah. So this implies there exists, let's say, identity tilde, such that there exists a unique map identity tilde. In fact, it's unique, such that this map identity map from R to, so maybe I'll write it differently. This map R to R, which is identity of factors through S inverse R. Yeah, so this is the phi map, and this is the identity tilde map. Yeah. So this exists and is unique. That is what a universal property of localization tells us. Yeah. So what we get is phi composed, phi followed by identity tilde is identity. Yeah. So we get so that tells you that I mean it tells you have a left inverse of phi. Now one also has to do the right inverse. So let's see. So I'm checking if I can do it through diagrams itself. So one can do it using elements, but trying to do it.
Sir, can the uniqueness help over here?
Yeah, so uniqueness is what we haven't used, yeah? Yeah, so that's what I'm thinking. Yeah, so I guess, yeah, one can use uniqueness. So remember, identity tilde is unique, yeah? And then there is another map from, so what is the other map from? So you have a map from R to S inverse R, but
Sir, R by 1 goes to R, that will satisfy, but to prove that it's a map,
yeah,
again we have to use the units. I mean,
yeah, exactly. Yeah, so let's just try to show that identity tilde is an isomorphism, yeah, instead of worrying about this in yeah. So of course, identity tilde, I mean, since P composed, so it's obviously surjective, right? Because identity is surjective, yeah. So note identity tilde is surjective because identity tilde composed phi is identity and identity is surjective, so it is surjective. So you only have to show that the kernel is trivial. Yeah. So and even that is okay. Note that kernel of phi is trivial because it contains non zero. So kernel of identity tilde composed phi is 0, yeah, because that is identity. And what is kernel of composition of 2 map? It's identity tilde inverse of kernel phi. Yeah. That is how you compute the kernel of composition of 2 maps. Yeah. So you look at kernel phi. So what is kernel? Basically, it's okay. So kernel of any map is basically identity composed phi inverse of 0. Yeah, which you can think of it as identity inverse, identity tilde inverse of phi inverse of 0. Yeah, and phi inverse of 0 is kernel of phi. So this is what you get. Yeah? So this is the explanation for this thing. And but kernel phi is 0. So this is and this is same as identity tilde inverse of 0 is 0. Right. So the or rather I should write implication here. This implies this is 0, but this is precisely kernel of identity tilde. Yeah. So that tells you that identity tilde is injective. So we sort of did it without using elements in some sense. Identity tilde is injective. Well, of course, you can do it using elements as well. Yeah, you can say where the various elements go and try to show surjective and injective directly. Okay, so it's somewhat satisfactory. Okay, any questions?
So in the identity tilde composed phi of inverse 0, it should be phi of inverse of identity inverse.
Yeah. Oh, sorry. Yeah, I made a mistake here. That's right. Right. So this is yeah. Sorry about this. So this is kernel identity tilde composed phi, and this should be phi inverse of. So it goes in the opposite direction. Identity tilde of inverse of 0. Yeah. Okay. So then there is the argument is a bit shady. So this is phi inverse of kernel of identity tilde. Yeah, is 0. Yeah, but even then also then it becomes only one step. Yeah. So phi inverse of something is 0. That tells you that that guy must be 0. Yeah. So this implies kernel of identity tilde, of course, contains 0. Yeah, but it can't contain more than 0 because then yeah, phi inverse will be bigger. Yeah, so this implies kernel of. So here, because here phi is injective, so since phi is injective. Yeah, so phi is injective means it can't have in this kernel of identity can't have more than one element. Yeah. Okay. So ordinarily phi inverse of something bigger could. So if phi maps a lot of things to 0, then of course phi. Yeah, so I don't think you need phi's injectivity. We don't need injectivity, right?
So because like for any ring homomorphism, phi 0 equal to 0, and that's the only thing which we need.
Yeah, so you don't even need phi's injective here. Okay. Yeah. So 0 has to belong there, and there can't be anything else. Okay. So what we get is kernel of identity is indeed 0, and that's it. Okay, any questions? So you can as well check it element wise. Yeah. So you can check R over 1. So the map, in fact, you can check what it does. So R over S will go to, so remember this sense. Uh, so by our description, R over S will go to S. So this S inverse, identity of S inverse, which is just S inverse times R, which is again R over S. Yeah. So it is the identity map in some sense, written in a funny way. Okay. Okay. So it is transparent. I'm just trying to make it look more complicated because I wanted to do it via diagram. But if you write it directly what this map is, then of course this is trivially an isomorphism. Okay. Any questions? Hopefully I haven't
Sir,
confused.
in the proof, where did we use anything about phi?
We use the fact that is in the diagram proof, you mean, right?
Yes, sir. In this.
Yeah, so we use the fact that identity tilde composed phi is identity. Yeah. So so phi is so this universal property works only for phi. It doesn't work for arbitrary map. So R to S inverse R is the natural map, and this map has the universal property, this phi. So we showed that this will be an isomorphism. So when we compose
Here we have basically shown that identity tilde is an isomorphism.
Identity tilde is an isomorphism. That's why we have showed that. I see. We wanted to show phi is an isomorphism. Yeah.
Yes, sir.
Okay. Yeah, right. So we want to show phi is an isomorphism. Sorry. So that's why it's going. Yeah. Sorry. Okay. So let's try to show. Yeah. So maybe that is. Yeah. So why are we trying? Why was I trying to show identity tilde is an isomorphism? I mean, that is also going to be an isomorphism because it's the other inverse. But first thing to notice is that, okay, so maybe I'll not try to confuse anything. Let's just do element wise, yeah? So phi is injective is clear, yeah? Phi is injective.
It's an isomorphism, then phi is an isomorphism because its composition is an isomorphism, is identity.
That need not be true.
No,
The
composition.
left inverse is there.
Yeah. So you have to say both identity composed phi and phi composed identity both are
No, but because identity tilde is an isomorphism, you can left multiply the equation by identity tilde inverse. Then
that is true. Yeah. So then you will no identity tilde inverse. Identity followed by identity tilde inverse. Yeah. So if you show identity tilde is an isomorphism, then of course composition of two isomorphism is an isomorphism. So that also will tell you that. Yeah. So that way also one can say. Yeah. But one can do it directly as well. So I didn't mean to make things more complicated for you guys. Yeah? So first thing is phi is injective is okay because since I don't know as since
That's right from the composition.
that's just from the composition. Yeah. So surjectivity is something which we'll have to argue here since identity tilde composed phi is injective. Is injective. And secondly, phi is surjective because so let's take R over S. So maybe I'll do it elements wise. So R over S in S inverse R. Then R over S is equal to R over S times so S over, so which way I want to do? 1 over S over, so I want to show is phi of something, yeah? So it's phi of R over S is, yeah, R over 1 times 1 over S. 1 over S, yeah, which is equal to phi of R times phi of S inverse. Yeah, and remember note S inverse belongs to R. So 1 over S, we can also write it as S inverse over 1. That is what I have done. Yeah. So maybe one can go a step in the middle. So this is this is R over 1 times S inverse over 1. Okay, which is phi of R times phi of S inverse. Okay, so this is how you can show surjectivity.
Regarding like Anupam's argument about using the composition, I think that doesn't work.
Why?
Because phi is equal to identity tilde inverse identity. That means phi is an isomorphism from R to image of R under phi. We still don't know that image of R is the whole of
whether it's surjective or not, yeah? Yeah,
yes,
so surjectivity somehow we'll have to argue. Yeah. So you just get a left in. So I mean, identity is an isomorphism only tells you that, yeah, so phi has a left inverse, right? That is what we get. So for surjectivity, we need some sort of right inverse argument. Okay. So maybe one can do it via diagram as well, but I didn't, I thought this should be straightforward, so I didn't think in advance. But yeah, there should be a way to do it directly. So, yeah, so somehow one should use the fact that identity tilde is unique, get the argument directly. So you can also think about it. I'll also think about doing it through diagram chase. But through elements is okay, right? The argument is fine with the aid of elements. So there should be a what is called functorial way of doing it, which is through diagrams. But let's not worry about it now. Okay. So so that proves that if S consists of units, then this map phi is indeed an isomorphism. Yeah. So that means you're not getting anything new. Yeah. S inverse R is isomorphic for. Okay. So let's see. So the next goal was to show some more examples with various S in mind. Yeah. So I don't know why it's coming this way. Okay. Anyway, yeah. So this part is gone. But okay, you saw the argument, yeah. So next example is, so we had taken various examples of S, yeah. So one was complement of 0 in an integral domain. The other one was you can take 1, x squared, and so on. And there were a bunch of other examples. Let me just go to that lecture and see what were some of the other examples.
Excuse me, sir.
Yes.
Sir, I was just thinking of an argument.
Yeah, tell
Just
me.
like fact using uniqueness, sir. If we can show this thing that if our original ring is not a singleton, that is, our ring is not trivial, then there this unique left inverse implies it's a bijection.
Yeah, yeah. So formally meaning, yeah.
Yes, sir. So like if we say, suppose it's not a bijection, then because it's there is a left inverse, that implies our phi is an injection. It's an injective function over here.
Yeah, phi is injective is okay just from this.
So it is not surjective.
Yeah.
Because if it's not a bijection.
Yeah.
And then if it's not surjective, then we can find two different left inverses just using the elements which are not in the image. That can be mapped to anything. And because it's not a singleton over here, the domain set, we can have at least two. But over here, we know that there is a unique left inverse.
Yeah, so
that implies,
yeah, so how do you get two different left inverses?
because a ring is not a singleton.
Okay, so probably this can be done. So yeah, so maybe you write it down properly, and then you can send it to me. Yeah.
Okay, sir.
Yeah. Okay. So let's get to this example of a field of fractions and localization. So I wanted to see all the examples we were thinking about of multiplicative sets. Yeah. So yeah, so these were our multiplicative sets we were looking at. So of course, if S is 1, then or more generally consists of units, then it's not interesting. If S is R, then also it's not interesting because it contains 0. Number 3 also we saw. Yeah, so if you take S to be positive integers, then you can check that so of course in the new ring you get all the positive integers are invertible, so negative integers will be invertible. So using that you can say that this is as interesting as taking non-zero elements of integers. And then yeah, so this example we will discuss now, 5. Apart from that, yeah, so as I said, I union 1, this contains 0. So as soon as it contains 0, it becomes it becomes non-interesting because S inverse R will be 0. Yeah, and then this 7. So we'll look at the example 7 after this. Yeah, so only 5 and 7 are sort of remaining. So let's get back to our lecture 18. Yeah. Okay. So let's look at this example 5. So R is a commutative ring with unity. X is some element of R, and we take S to be 1, x square, and so on. Yeah, and then we will show that. So then what happens is S inverse R is akin to inverting X. Yeah, so you just want to invert. As soon as you invert X, of course, X square becomes invertible. Yeah. If U is a unit, U square is a unit. So you only have to invert U and that X. So then everything else becomes unit immediately. So what we'll this is more or less a notation. So don't think of it too seriously. So the what we will show is that S inverse R is this ring. So you can try to show. So this of course is makes sense, right? The numerator is the polynomial ring over R in one variable, and then you go mod this ideal generated by xg minus 1. Yeah. So maybe I'll just write where RZ is the polynomial ring. Over R. Okay, so so let's see a proof of this. So again, one can do it element-wise, but let's try to use the universal theorem. Okay. So we know that x will become unit, and in this ring, in the right-hand side ring, also x is a unit. Okay, so we can combine these two. So let's try to give a map from S inverse R to this guy using the universal property and otherwise. Yeah. So let's first consider this map. Actually, this is a natural map, so I'll write it as I from R to RZ mod XZ minus 1. Yeah. So what is this natural map from the ring R to this other ring?
E going to Ibar.
Yeah, so R going to R, its image here, yeah. So, or you can think of it as composition of these two maps. Yeah. So this I is R going to R bar. Yeah, R plus this ideal. If you write in terms of courses. So this is I is basically composition of these maps. So you have a natural map R to RZ, which is the inclusion map, and you have a map from RZ to RZ mod XZ minus 1. This is the quotient map. Yeah, Q. So we have these two map and their composition is I. Yeah, so this is what so composition of let's call it F. Let's not call it I. Yeah, so let's call this as I. And then F is basically first you apply I and then apply Q. Okay. So what does F do? So F of X is goes to something here. Yeah. So F of X is some element of R, and F of X is a unit. So I want to say that F of X is a unit here. Yeah. So note that F of X times note F of X times Z bar, yeah, which is same as Q of Z, yeah, is same as so X goes to under this map X in the under the first map I, X goes to X, so it's same as X bar times Z bar, yeah, which is same as 1 bar, since XC minus 1 belongs to the ideal, yeah, and belongs to the ideal generated by XC minus 1. Yeah, so this is something of a tautology. Yeah, so that tells you that, so this implies Fx is a unit. Yeah. So so once you know that this is a unit, you can get a map from so this implies there exists F tilde from S inverse R to RZ mod XZ minus 1, yeah, such that F tilde of, so I'll write it this way, R over S. So R over, yeah, so S is that set, yeah, so F tilde of R over S is F of R times F of S inverse, yeah, which by the way, so what for all, so I will make it more precise, for all S in capital S. But what is S in capital S? Is X power N for some N, yeah, or 1, which you can think of it as X power 0, yeah. So it's X power N for some N, yeah. And what is the inverse of X power N? Note S equals X power N for some N. For some N. And what is the inverse of S in Fs inverse? S may not have X power N may not have inverse in R, but Fs. So we know that Fx is a unit in this ring, yeah, RZ mod XZ in RZ mod XZ minus 1. But what is the inverse of Fs? What is the inverse of Fx? Is Z bar, yeah, Z bar. So what will be the inverse of Fs if S is X power N? is z bar power n, right? Yeah. So this is same as saying it's z bar power n fr. Yeah. So this is the definition of f tilde. So you got f tilde clearly. Yeah. So what we wanted to show is that this map is an isomorphism. Yeah. So we want to show that S inverse R is isomorphic to this guy. So in fact, we will show that this map itself is an isomorphism. Okay. So let's see. Yeah. Yeah. So maybe I'll give a map in the other direction. Yeah. Instead of doing it element wise this time. Yeah. So we have a map from RZ. So we have a map. Let's call it A from RZ to S inverse R. Yeah. So how to give a map from a polynomial ring? All we have to say is where does Z goes, and then we will have the map more or less. Yeah. So we should send Z to basically Z is inverse of X. So we should send Z to 1 over X, which makes sense in S inverse R. Yeah. So now where would we send? So Z should go to 1 over X. Yeah. And how do we send a general polynomial? So if we have a polynomial, an z power n plus an minus 1 z. So maybe I should call it some other map. I'm using it. So let's call it alpha. Yeah, as good as any. Z power n minus 1 plus a0. Where should this go? So I'm trying to define this map alpha. Yeah. So it should go to. So you just evaluate this polynomial at 1 over x, and that's what your map is. Yeah? So it should go to an over x power n. Sorry, x power n plus an minus 1 over x power n minus 1 plus a1 over x plus a0. So this is of course an element of S inverse R, yeah, because where AIs are an element of R. So A naught doesn't make sense, so I'll just put A naught over 1. Yeah. In S inverse R it doesn't make sense, so we put A naught over 1. So this is alpha is our a map from RZ to S inverse R, and alpha is a ring homomorphism. Alpha is a ring homomorphism. Why? Because it's an evaluation map. Yeah, alpha is since alpha of f is just alpha of a polynomial, maybe p. So alpha of p is, or maybe let's just write more suggestively, pz is just p evaluated at 1 over x, and that is what it is. And we have checked many times that such a map is always a ring homomorphism. So if you have two polynomials, pz and qz, then you just add them. So the evaluation behaves well. Yeah. So alpha is a ring homomorphism, and we know that xz minus 1. What is alpha of xz minus 1? This is x over x. So remember, x is an element of R, so this makes sense. This is a polynomial in RZ, and it goes to x minus x over x minus 1 over 1, which is 0. Yeah. So this tells you that the ideal generated by xz minus 1 is contained in kernel phi. Yeah. So as soon as you get this, then by the proposition which we proved before the first isomorphism theorem. In fact, one can show that the kernel is exactly this, but I don't have to do that hard work because I already have the map in the opposite direction. what we get is alpha induces a map alpha tilde from RZ mod xz minus 1 to S inverse R. And what is this alpha tilde? Alpha tilde stands pz bar to the image of alpha. Yeah, so alpha of pz, which is p of 1 over x, p evaluated at 1 over x. Yeah. So alpha tilde sends pz bar to p of 1 over x. And so we check that so in the first isomorphism theorem. So this is the implication of maybe it's like first isomorphism theorem, but it was a prelude to first time. So first isomorphism theorem was a corollary of this statement. Okay. So we have got maps in both direction, and then you just check that these two are inverses, f tilde and alpha tilde. Yeah. And for that you have this explicit description of both the maps. Yeah. So check. So let's just check this. Alpha tilde composed f tilde. So f tilde is a map from S inverse R to this guy of, let's say, an R over S. Where does it go? So f tilde of R over S is z bar power n fr. Yeah, so this is what the description of this is, and so I have to apply alpha tilde to it. And alpha tilde of fr is some element of what was fr? What is f? F is this map, yeah. So fr is basically r, yeah. So there is nothing to. So I should have written it's just r. Fr, remember, f is this map I followed by quotient map. So fr is basically r bar. So let me just write it r bar here instead of writing it in a funny way. So this is. Yeah. So maybe I'll upgrade it here as well. So this is just z power n r bar. Yeah. And what is alpha tilde of z bar power n r bar? So you just look at a representative of this and evaluate at 1 over x. And what is a representative of this? So this is you just substitute. So you have to evaluate replace z by 1 over x. So this is r times 1 over x power n. Yeah. So it's r over x power n. Yeah. If s is x power n. Sorry. So so this was under the assumption that s is x power n. If s equals x power n. So s has to be of the form x, some x power something. So if s is x power n, then we get this, which is r over s again. Yeah. So s has to be s is an element of so S is an element of capital S, implies S equals x power n for some. Yeah. So we get alpha tilde composed f tilde is identity, and similarly the other way around. F tilde composed alpha tilde. So you just look at the of some guy. So what is alpha tilde is typical element is pz bar. Yeah, this is how an element in this ring look like, rz mod xz minus 1. This by definition is p of 1 over x. Yeah, and one has to do f tilde here. So sorry. So f tilde of this guy. And what is f tilde of p of 1 over x? So p is some polynomial, yeah? So we'll take this as a representative polynomial, a n z power n, a n minus 1, z power n minus 1, and so on. So this is a n over x power n plus a n minus 1 x power n minus 1 plus a0 over 1, where let's say pz is a n z power n up to a0. Yeah, so if pz is this form, then this is what we get. And then you yeah, so I have to get to identity. So sorry, so p of 1 over x is this. I still have to apply f tilde. And so this we can write it as so what is this f tilde map? F tilde maps r over s to z bar power n over r. So I have to write it as r over s. Yeah. So the way to write r over s is we take x power n common. Yeah. So this, we know how the addition works here. Yeah. So this is going to be x power n a n. So you just check that this is the one in the bracket is a n plus a n minus 1 x plus a0 x power n. Yeah. So this is same as this in S inverse R, and hence what you get is this is same as so yeah, so this is z bar power n. So so this what you'll get is z bar power n times r bar. Yeah, so r is this guy, so it's z bar power n. I didn't think it should go this much, but it's going anyway. So let's just write it down. Minus r bar is this guy, a0 x power n bar. And y is the same as yeah, so one has to eventually use the fact that these two are I mean the ideal is xz minus 1. Yeah, so you just multiply this through, what you get is a n z bar power n plus a n minus 1 x bar z bar power n minus z bar power n, but remember x bar and z bar is 1. So what you get in this ring, so what you get is z bar power n minus 1 up to a1 z bar plus a0 bar, which is so yeah, so let's just put bar everywhere, which is same as pz bar, pz pz bar. Yeah. Okay, so this is what so again alpha tilde f tilde composed alpha tilde is again identity. Okay, so that completes yeah, so I thought it will take less time, but it took a little longer. So that completes the proof that these two are actually inverses to each other. Okay, so since I had already written on this side, I decided to go full-fledged on this one. So but when I post note, I'll split the spot somehow. Okay, so board work became messy. Every time I try to write in advance, things become a little bit messy. Okay, any questions? Okay, so yeah, so we are not, so we are way past the break time, and I wanted a break so that it's easier for everyone to concentrate. But let's skip the break today, yeah. And so I'll just define local rings, and give examples, and we'll prove this proposition next time. Yeah. So this part of the discussion will come in more details next time. Okay. So what is a local ring? So, so a commutative ring with unity is called a local ring if it has exactly one maximal idea. So, so most rings which we see, Z or polynomial ring over Z or polynomial ring over a field Qx, etc., they are not local ring. They have many maximal ideas. But we have seen some examples of rings which are local rings. Yeah. So, can you give me one example of a local ring? A ring which has only one maximal ideal?
So the formal power series or any valuation.
Yeah, so that of course, if from your homework you have seen that valuation ring is an example. So, but before that, there is even more simpler example. So maybe I'll write. Yeah.
Fields.
Fields, exactly. So first example, first kind of examples is fields. Yeah. So it has only, I mean, it has only two ideals. One is the whole ring, and one is the zero ideal, and zero ideal is maximal. So fields are first examples of local rings. And then, of course, you mentioned valuation rings. So let me just put here valuation rings. Okay. But yeah, so there are modes. Yeah. So third kind of example is Z mod something. So what should I put here? So if I put PZ, where P is a prime, of course it becomes a field, and hence it's a local ring. Yeah.
4Z.
Say that again.
4Z.
4Z. Yeah. So that's so 2Z of course is a local ring because it's a field, but even Z mod 4Z is a local ring. Okay. So what are the maximal what are the ideals of Z mod 4Z is 0. Ideal generated by 2, and that's it. Yeah. So these are, and then the whole ring. Yeah. So these are the only three ideals. And Z mod 4Z we know is not a field. So in fact, what you can show is that more generally, Z mod P power NZ, yeah, n greater equal 1 is a, and P prime. So that's important. And P prime. So these are some local rings. So these are some examples which you have already seen of local rings. Okay. But we'll see more examples. Yeah, so maybe let me not talk about this proposition at all. Yeah. So we'll see more examples and first, and maybe then. So maybe I'll mention one more example, and this proposition I'll just move it to the next lecture. Yeah. So let me not discuss this proposition. Let's just get to this next example 4. And so this will be when we take this example 7. Yeah. So meaning when we take S to be complement of a prime ideal, then we will get. But I don't want to do it in that generality today. So I'll just talk about this guy. So Z and is our ring R, and if we take S to be this guy, this we have already discussed, 2 square, etc. Then what is S inverse R? Is just a ring which we get when we invert 2. Yeah, so this is actually Z and half, Z adjoint half. So this makes sense. So R 1 over X doesn't make sense because you don't know whether, whether R is an integral domain or not. So this will make sense as a subring of Q. Yeah, so I can think of it as a subring of Q. So this makes sense. And then so here also this would R1 over X will make sense if you know R is an integral domain, then you can just think of R1 over X as a subring of the fraction field of fraction. Okay. So you get this thing. when you do this localization. So you invert everything. So you look at fractions. So the description is A over B, where B is 2 power n for some n. Yeah. Another ring which you can cook up using 2 is somewhat. So you allow. So here you are allowing denominators which are powers of 2. In the other, you allow denominators which are co-prime to 2. Okay. So. So this is sorry. So this is not an example of a local ring. This is example of some ring. Yeah. So maybe I'll not do 4, but 4 comes here. So this is maybe a corollary to the previous result, which we could instance of the previous result. But the final 4 is this thing. So you take R to be Z and S to be complement of the ideal generated by 2. Yeah. So odd integers. Yeah. So this is R minus 2, so Z minus 2Z. Come on, Z minus 2Z. Okay, and then if you do, so remember odd integers directly you can check is closed under multiplication and 1 belongs there, right? Product of 2 odd integers is odd integer. So what is S inverse R? So so you are inverting things in S. So they are all going to be in field of fractions, right? If you invert everything other than 0, then you get Q. So this you can think of it as subring of Q. And what are the kind of fractions you put in A over B, such that B comma 2 is so B is odd. A, B are integers and B is odd. So that is the definition of S inverse R. Yeah? We take these kind of elements. Okay. So so here we were taking denominators which were powers of 2. Here we are so these 2 rings are in some sense very different. Yeah. So and here the good thing about this ring is this has only one maximal ideal. Okay. So so of course. So let me just tell you what that maximal ideal is. So, so what are the maximal ideals in Z? So the maximal ideals in Z is P times Z, where P is some prime. Yeah. So this is a ring between. So S inverse R is a ring between Q and Z. Yeah. So this lies somewhere in between. So what happens, so I mean, of course, in Q, there is only one maximal ideal 0. What happens to the maximal ideals here in Z? In Z, when you go to Q. So if I take P, the point is P becomes invertible in Q. So that so the maximal ideal becomes the whole ring when we pass here. So similarly, if we take P some odd number and try to do here, then that P becomes a unit. So the ideal generated by that P is the whole ring. Yeah. So the only thing which doesn't become a unit is an even number. Yeah. And an even number is always contained in this ideal generated by 2. So 2 belongs here, or 2 over 1, if you like, will belong here. Yeah. But if we sort of identify the image of Z here, 2 also makes sense. So 2 is an ideal in S inverse R, and it is going to be a maximal ideal. So if you go mod 2Z, you'll get, you go mod 2, then 2 is a proper ideal because 2 is a non-unit, so you can't get the whole ring. And if you go mod 2, you will see that you'll get Z mod 2Z. Yeah. So this will be a local ring. So this is so what you get is 2 the S inverse R. 2 S inverse R is a maximal ideal of S inverse R, and in fact it is the maximal ideal. the maximal ideal. So S inverse R is local. And this has a notation. So this is usually denoted by Z2. Okay. So this is Z2. So we'll talk about this construction in the next class in more details. Okay.
2 means 2 by 1, right here.
Say that again. Yeah, 2 means 2 by 1. So here we are identifying Z as a subring of Q. Yeah.
Okay.
So 2 by 1, everything makes sense. Yeah.
Okay.
Any other questions?
So is this related to the fact that 2Z is a prime ideal?
Yeah, in the sense that 2Z is a prime ideal, so Z minus 2Z is a multiplicative set. So we can do this calculation. So for any prime ideal, we can take S to be complement of that prime ideal and invert those elements. And then what we'll get is a local ring which has only one prime ideal, one maximal ideal, which will be generated by the elements of this prime ideal. Okay, or images of elements of the prime ideal P. So next time we will see this construction, and we'll also relate ideals of R and S inverse R. Yeah, and that will tell us how things work.
Okay, sir. Thank you, sir.
Okay.
Sir, and one more thing, sir. I think the quiz has not been removed yet from the Moodle platform.
What hasn't been removed?
So the quiz.
Which
So
quiz?
it was scheduled to be tomorrow.
Oh, quiz 2. Yeah, I'll remove it. Don't worry about it. Yeah, so I'll just change the time to Tuesday. So tomorrow we'll do this this class as usual. Hopefully we'll be able to wrap this localization chapter, and then we'll have a quiz on Tuesday, and then after the break we'll reconvene and do something else. Okay.
Thank you, sir.
No. Anything else? Okay, so if there are no more questions, let's just stop.